welcome everybody to the session on advances and insights from Satellite-Defined PM2.5. So we have two presentations. It'll be 15 minutes each, and then we'll have a discussion afterwards. So first we have Randall Martin.
Thank you. So it's an honor to give this presentation. And if I understand my charge correctly, I should be providing you with some technical underpinnings describing the satellite-derived PM2.5 data set in order to understand its applicability. So I'll have four main themes here. The first, emphasizing the integration of multiple satellite aerosol optical depth data sets in order to inform this estimate. The second is about a ground-based measurement network that we're using to underpin the evaluation of the aerosol optical depth PM2.5 data set. The third is then I'll allude to briefly some insights in environmental health and epidemiology. I think we'll hear more about that from Susan subsequently, and a few words about ongoing activities. And this audience well understands the health effects associated with PM2.5, the large gaps in ground-based prevention, and nonetheless, the need for some measurable information to inform PM2.5. And then that leads us to turn to satellite remote sensing as our primary data source. Building upon that constellation that we heard about from John Haynes earlier this morning, with a growing suite of instrumentation that offers decades of innovation in examining that electromagnetic radiation in order to inform understanding of atmospheric composition and leading to increasingly precise and accurate information at increasingly fine resolution. And we're fortunate to have these several different data sets on aerosol optical depth, including the dark target algorithm with Rob Levy having leadership roles. I don't see him here, or Andy Sayer also having leadership roles on the deep blue algorithm, as well as the MISER algorithm, which has a multi-angle capability to map out the aerosol phase function, determine the abundance, or a MIAC algorithm. And all of these instruments and algorithms have strengths and weaknesses that vary with location and vary with time. So an overarching theme of our effort is to evaluate the quality of these different data sets versus a ground-based sun photometer network of AeroNet that accurately measures aerosol optical depth. And you're seeing here an example evaluation of two of the different data products, dark target in the top right, MIAC in the bottom left, for an example month of July. And the center of each concentric circle is showing the retrieved quantity. The exterior is showing the measured quantity from AeroNet. And you should discern a high degree of consistency of both different data products with each other, as well as with the ground-based measurement network. And this makes sense given the maturity of both of these algorithms. Nonetheless, there are differences between these different data products that vary with location and vary with time. And those differences offer statistics about the uncertainty, describing the uncertainty for a specific algorithm at a specific point in space and time. Our next step is to aggregate this information in order to determine a globally complete assessment of uncertainty. And to do so, we'll leverage the relationship of uncertainty with surface reflectance, the driver of the uncertainty in retrievals of aerosol optical depth. We'll also, so we'll align that with land type for that purpose. We'll inversely weight by distance in both space and time to produce an overall composite estimate of uncertainty. You see that on the bottom right for the dark target algorithm. This algorithm is designed to have low uncertainties over dark vegetated surfaces. You'll see that over the eastern part of the United States, or to have larger uncertainties over bright arid surfaces, and that's apparent over the western part of the United States. So this approach allows us to characterize the uncertainty for each different product. And then the next step is to aggregate that information, weighting these different data sets by their relative uncertainty to produce an overall composite estimate of aerosol optical depth, and then quantitatively relate that aerosol optical depth information to ground level PM2.5 using a chemical transport model, HAQAST. For that purpose, we'll coincidentally sample that model with each individual retrieval and from each different instrument and algorithm. Overall, that geophysical approach yields this, what we call a geophysically based PM2.5 estimate determined from the remote sensing and modeling alone. And that explains about 80% of the variance in the ground-based measurements. A subsequent statistical fusion explains an additional 10% of that variance, leading to what we'll call a hybrid estimate. Now, there are several reasons why aerosol optical depth turns out to be a useful indicator of PM2.5, and 4 of which are listed here. The first is that because these retrievals are conducted at visible wavelengths where the atmosphere is highly transparent, a columnar observation from space contains information all the way down to ground level. The second is that as the aerosol vertical profile has a tendency to be peaked down near the surface, that a columnar observation is often dominated by what's happening within the lower mixed layer, the air that we breathe. The third is that the interaction of those particles with light happens to exhibit a resonance when the size of the particle is comparable to the wavelength of light. That happens to coincide with the accumulation mode size distribution for visible light. And so that's just fortuitous in terms of sensitivity to the PM2.5 size range. And the fourth is that the intraday variability in PM2.5 is generally small, within plus or minus 10%. So a satellite observation at a specific time of day, either late morning or early afternoon, has a tendency to be close to a 24-hour average. Now, we don't directly assume any of these relationships and rather attempt to quantitatively account for deviations from these relationships. Rather, their existence facilitates the relationship of aerosol optical depth, PM2.5. And as part of that evaluation or an endeavor to relate aerosol optical depth to PM2.5, we'd like to evaluate our simulation of that. It's a complex relationship function of several parameters, such as the aerosol vertical profile or the composition-dependent relative humidity. And you're seeing an example of that simulated relationship in the model. But despite that desire to evaluate it, and despite the hundreds of ground-based sun photometer measurements or the thousands of PM2.5 monitors, only a handful have been historically co-located. And that has motivated the creation of a surface particulate matter network designed to measure that quantity. It builds upon the well-respected sun photometer network, the AeroNet, that accurately measures aerosol optical depth from the ground. And in densely populated areas of relevance for health, adds a PM2.5 monitor. That monitor has been designed to be highly autonomous to reduce the burden on the remote operators, featuring this removable cartridge that can be preloaded here in our central laboratory at WashU, shipped off to each different remote site where the operator just simply needs to insert that cartridge into the instrument, let it run unattended for a period of time as it cycles through the different filter slots, avoiding a traveling blank. Upon completion of sampling, the operator can remove that cartridge, ship it back to our lab for analysis of the wealth of chemical composition information contained on those filters. The instrumentation package also features a nephelometer that offers high temporal resolution, but more importantly, offers this optical information that's of value to decompose a satellite optical measurement into mass. Thanks to a number of partners worldwide, we've been fortunate to sample at about 30 sites to date. Again, site locations prioritize densely populated areas of relevance for health. Although this network was designed explicitly for the purpose of measuring that relationship of aerosol optical depth, PM2.5, it has also become the only global chemical composition network for PM2.5 globally. So that's offering information about sources or also for model evaluation, and is now beginning to underpin planned missions such as serving as the validation data set for the Maya mission that is forthcoming. The result of those three major themes, beginning with the satellite remote sensing data, the model to relate that aerosol optical depth to PM2.5, and then ground-based measurement data to further evaluate and improve that, those estimates, yields the resulting data that you see here for North America on the top and for Asia on the bottom. And you should observe this high degree of spatial and temporal variability across these domains. Notice a factor of 5 or 6 difference in the color scale between North America and Asia. One of the exciting findings that's being revealed from this data is going to be highlighted by a poster led by Charlie this afternoon that identifies a global success story in reduction in PM2.5. If one looks at the first decade of this millennia, one sees in the top left, one sees that most countries in the world exhibited an increasing tendency of PM2.5. As you see in the warm colors, the major exception is in North America and to a lesser extent in Europe. Then in the most recent decade, one sees a reversal in that tendency, with most countries exhibiting a decrease in PM2.5 or statistically insignificant trends. The prominent change is in China, where one sees a very steep increase in the first decade and a very steep decrease in the second decade. The top right panel is showing you the population weighted aggregation globally, and one sees then the driving role of China that's reinforced by this contribution from multiple countries and sustained reductions in countries that did feature those reductions, such as in North America. We've been fortunate to work with colleagues in environmental health and epidemiology to explore the association of PM2.5 with a variety of health endpoints. One of which is to examine the shape of the exposure response function, especially at low PM2.5 concentrations. That's of relevance for informing policy or such as standards or guidelines set by nations or the World Health Organization. Another area in which we're devoting attention is understanding the implications of the systemic inflammation response that may manifest into outcomes that are not mortality outcomes per se, but may impair quality of life, such as dementia or cognitive development, or diabetes can have mixed outcomes there. There are outcomes related to COVID-19, and I hope we'll hear about environmental justice from Susan later in this session. In the time remaining, I wanted to share with you a few of the ongoing activities in this space that are focused on improving the estimates further. One of which is preparation for beers in preparation for the termination of Terra Aqua. And you've heard me speak about that briefly in October. Another one is focusing on processes that would affect the relationship of aerosol optical depth with PM2.5. A poster led by Yanxin Li will examine the intraday variability in PM2.5 and how that might be affecting the AOD to PM2.5 relationship. A poster led by Haihui Zhu is examining the relationship of aerosol optical depth with aerosol size, and thus can be used to improve the estimation of aerosol optical depth in the simulation. Some ongoing work led by Inderjeet Singh is examining the role of dust non-sphericity and modeling the aerosol optical depth more accurately. Dandan Zhang is examining the relationship of aerosol optical depth to PM2.5 at increasingly fine resolution. Siwen Shen is examining the role of machine learning to improve the statistical fusion with ground-based measurements. And Dipanshu Chatterjee is examining sources affecting PM2.5 with particular attention over South Asia. I'll highlight one result that is more difficult for Dandan to show in a poster, showing this fine resolution simulation of aerosol optical depth with dividing the Earth's atmosphere up into 200 million boxes to yield a 12-kilometer resolution simulation that contains information on the chemical composition of PM2.5 as well. And you should observe this pronounced heterogeneity that is important in sampling to understand that relationship of aerosol optical depth with PM2.5. Chemical components, briefly: yellow for mineral dust, blue for sea spray, green for organics, black for black carbon, and red for the sulfate nitrate system. But as I run out of time, I want to leave you then with some growing confidence in the inference of PM2.5 from satellite remote sensing and modeling. The value of integrating aerosol optical depth from multiple instruments and algorithms in order to produce a more robust estimate of aerosol optical depth. We see indications of an emerging reversal in global PM2.5 that hopefully will be sustained in the near future and are contributing to investigation about some of the health effects of PM2.5 with particular attention at low concentrations. And with that, I'd like to thank my research group who makes this science possible, and thank you for your attention.
Any other question?
Yes.
So our next speaker is Susan Anenberg from the other Washington University. Washington University.
We just need someone from University of Washington, Chris. Okay, well, thanks everyone. Really great talk, Dr. Martin, and I'm really glad that we did this in this order because almost everything I'm going to show you today builds from the work of Randall Martin and his group here at WashU and at Dell. So what I'm going to do today is focus a lot on the interactions that we have had with stakeholders in using this data to answer relevant questions about health and environmental justice. So I think most of us have seen something like this, some iteration of this result, that air pollution continues to be a leading health risk factor in nearly all countries. And the current estimate from the Global Burden of Disease Study from the University of Washington Institute for Health Metrics and Evaluation is that air pollution is the 4th leading overall risk factor for human mortality. That's not the 4th leading environmental risk factor. That's the 4th leading overall risk factor, just behind high blood pressure, tobacco, and dietary risks. And if you look at the fractional contribution of air pollution to this range of diseases at the bottom of the screen here, this is not a minor player. This is a preventable risk factor that we can really make a major dent in some major causes of mortality if we were to address air pollution. But what I want to focus on is how do we build an estimate like this? How do we do the exposure assessment, and how has that evolved over time to lead us to this knowledge about the contribution of air pollution to human mortality? If you have been at these meetings for long enough, you've probably heard me talk about this before. So I apologize if I've already shown this, but it's been a few years, so maybe we have some new people. So let me just kind of step through a little bit of the evolution of the PM2.5 disease burden assessment in global burden of disease assessments. So back in 2004, I don't want to date myself too much, but I was graduating college. The leading estimate at the time from the World Health Organization, which was doing the global burden of disease study, was that there were 800,000 premature deaths associated with urban PM2.5. And the reason this was limited to urban areas is because that's where we had the ground monitors. And you can see the map here is where we had monitors. A lot of these actually were PM10 monitors, which then had to be converted to PM2.5. So you can see that most of the world was left uncounted in this assessment. And it was actually my master's project in 2010, where we used a global chemical transport model to fill in the gaps between the monitors. And we estimated about a 5-fold higher burden of disease, burden of mortality from PM2.5, about 3.7 million PM2.5 deaths, and about 700,000 ozone deaths every year globally due to PM2.5 and ozone. This is actually, I remember going to an AGU conference and speaking in the same session as Aaron Van Zonkelaar, who had presented a very similar estimate using satellite data. And now that we can integrate satellite data with the global monitors and ground observations, not only do we achieve this full global coverage, but we also get the high spatial resolution that Randall was talking about that enables us to tease out, what are the high concentrations that are very co-located with very densely populated areas of the world. So every year, basically, now the global burden of disease study is providing new estimates of the burden of disease from PM2.5 using refined methods that, again, do this integration between the satellite data, the global models, and the ground monitors that Randall was just explaining to us. And I'm really optimistic about the future because, well, I had to cross out future, actually. I used to present this as the future. Now it's now because we have geostationary satellites. And we also have low-cost sensors, and we have mobile monitoring. And we have a whole new world of exposure assessment techniques that we can integrate further and really get even better information about what people are breathing all around the world and how that contributes to their health. But going back to that global coverage and high spatial resolution, that's a huge advantage of our ability now to integrate satellite data with global monitors and global models and monitors. And so what we can do is tease out, for every city in the world, and there's about 13,000 of them, for every city of the world, what are their PM2.5 levels? What are their ozone levels? What are their NO2 levels? And how is that contributing to public health impacts in those cities? And how has that changed over time? We can actually do this now for several decades. So this is work that was led by Dr. Veronica Sutherland, Dr. Arash Moheg, and Dr. Dani Malashak to estimate these concentrations and disease burdens in all 13,000 cities of the world. We've sent this data to the Health Effects Institute, and they published the first Air Quality and Health in Cities report, which goes along with their State of Global Air activity. And it provides now information to cities that never before had data because they lack monitors or monitoring was done, but maybe there's only a handful or one or three or so monitors in the city, or maybe the monitoring was only over a several week period and not long enough to really capture the full annual average of PM2.5. So we're providing information to cities that really never before in many cases had this level of information. But another use case for this data is to work with global networks of cities. And there's actually now several global networks of cities that have formed to address either air quality or greenhouse gases or both. So we've been working directly with C40 cities. It's a network of almost 100 mayors around the world that is committed to deep decarbonization. And they actually have, if you dig into their business plan, they actually have a metric for the number of C40 city residents enjoying improved air quality, and that's based on PM2.5. So many of these countries that have joined the C40 network, these are large, forward-thinking cities that really want to cut their greenhouse gases. It's a self-selected group of cities that probably has some degree of local monitoring. But nevertheless, it's helpful to provide an additional measure of PM2.5 beyond what's available from those ground monitors. And so they're now using our estimates of satellite-derived PM2.5 estimates in 13,000 cities to track how cities are performing in terms of their PM2.5 concentrations. Another way they have used this, and this is building on a partnership with Chris Tessum and many others as well, is in their climate action planning program. So several years ago, C40 was engaged in the largest urban climate action planning program worldwide, covering about 700 million people. And these are individual cities that are developing pathways to cut greenhouse gas emissions. They looked at business as usual. They looked at ambitious greenhouse gas mitigation. And they previously did not have a way to integrate PM2.5 into their climate action plan. So they had very detailed assessments of CO2 emissions, where those emissions were coming from, and how those would be affected by the mitigation plans. But what about the PM2.5 emissions that we know are emitted anytime, or emitted alongside CO2 anytime we're burning these fossil fuels? So this large partnership of institutions and researchers listed at the bottom came together, and we helped these cities integrate PM2.5 into their climate action plans. I'm just showing two example pilot cities that we worked with, Buenos Aires and Johannesburg. And this used the satellite-derived data set from Randall Martin's group to give them an estimate of the present day levels of PM2.5. and then the global INMAP model that Chris Tessum and Julian Marshall developed to turn that to project in the future how PM2.5 concentrations could change with these different scenarios of greenhouse gas mitigation. And you can see this is very policy relevant and useful to them. So in Buenos Aires, they saw that the ambitious scenario of reducing greenhouse gases dropped their PM2.5 concentration from about 12 to about 8. At the time, that was below the World Health Organization air quality guideline, but that has since been revised from 10 to 5. So they're still above that, but still quite a big drop. In Johannesburg, they looked at the percent of total PM concentration reduction on the X, and then the percent of total CO2 emissions on the emission reduction on the Y. And you can look at which individual measures of reducing greenhouse gases gives you the biggest bang for the buck in terms of both CO2 emissions and PM2.5. The other thing we can do with this full geospatial coverage of satellite-derived PM2.5 is look within individual cities. So everything I showed up until this point is, a snapshot of all 13,000 cities globally. Just one estimate per city is like a city average. But what about all the neighborhoods within cities? And we know that cities are experiencing quite a bit of inequality, health inequality, income inequality, racial segregation. And so we partnered with the DC Department of Energy and Environment and the Office of Health Equity, who are very concerned about the approximately 20-year life expectancy differential between some neighborhoods in the southeast quadrant of the city versus neighborhoods in the northwest quadrant of the city. And that's a 20-year life expectancy differential between people who live just 3 or so miles away from each other. And they wanted to know how much is air pollution contributing to that inequality. So we estimated PM2.5 attributable mortality, again, using the PM2.5 concentrations from Randall Martin's group. And we can see that the map of PM2.5 mortality risk lines up almost exactly with the map of racial segregation in the city, with the eastern half of the city being predominantly Black and the western half of the city being predominantly white, and the western half having a very low PM2.5 mortality risk, and the opposite for the eastern half. This was, this got a lot more traction beyond the journal article that we published on this. When NASA remade our map into a much more aesthetically pleasing version and put it on the Earth Observatory, and then it was tweeted and Insta'd all over the place, and it really reached a lot more people. But I think importantly too, it really helped the DC Department of Energy and Environment figure out, they actually had funds available from the Volkswagen Dieselgate scandal settlement funds. And they wanted to know, how do we use those funds to reduce emissions in the communities that need emission reductions the most? And maps like this can help inform those types of decisions. I don't know what happened to the bottom here, but that's Gage Kerr. And he's really taken this really in a very interesting pathway and shown that we can do this type of air pollution inequality analysis, not just for an individual city, but for all cities. Using, again, the high spatial resolution and full geospatial coverage of the concentration data. So what he's finding is that PM2.5 concentrations overall have declined, and mortality risks have declined along with it. And that's due to the very successful Clean Air Act and the regulations that go along with it. But PM2.5 disparities are increasing over time. So 1.32 is the ratio between PM2.5 attributable mortality in the least white census tracts across the US versus the most white census tracts across the US. And he's also compared this to NO2 attributable asthma on the right, and we see even much wider disparities for NO2 health risks compared with PM2.5 health risks. That's not to diminish the importance of the PM2.5 disparities. This is the biggest killer when it comes to the air pollution mortality risk. So something that we should all be very concerned about. And Dr. Tess Carter, who's standing in the back of the room there, presented on this earlier today, so I'll just try to breeze through it. But we do now have the Biden administration's Justice 40 initiative, which aims to deliver 40% of the overall benefits of investments in climate, clean energy, and related areas to disadvantaged communities. And they developed the CJUST tool, the Climate and Economic Justice Screening Tool, to help identify disadvantaged communities. There's a whole definition that goes along with this as well. So what I'm showing here is census tracts in the Chicago region. I just zeroed in on one just somewhat randomly and found that this is a community that is defined as disadvantaged in the CGES tool because it has greater than 90th percentile PM2.5 concentrations, and also is a low-income community. But as Dr. Carter showed earlier today, it really matters what we're using for PM2.5 concentrations. So she showed this earlier, I'm not going to go through this, but we have different spatial patterns when we're using different PM2.5 concentration data sets. This is for Los Angeles, Chicago, and Phoenix, using 3 different PM2.5 data sets, with the CMAC-F model being the one that's currently used in the CGES tool as well as in EJ-Screen. And we have about 1.5 million people who are identified as disadvantaged using both the 2 high-resolution data sets, PM2.5 concentration data sets that we examined, that were not flagged in the CMAC Fusion data set. So this just shows that it really, this is a very impactful decision. What's used for PM2.5 in these governmental mapping tools is a very high impact decision, because this is what's actually driving investments in communities in this administration. I'm really excited about the future because we're going to have tempo data coming online, hopefully next year or so. And we're also, I'm very pleased to be working with NOAA, who is developing the GeoXO geostationary satellite next generation, launched in the early 2030s. And they asked us, sorry about the bottom, but this is Dr. Kate Odell, who's leading this work. They asked us, can you help us understand the benefits of providing atmospheric composition data from a geostationary satellite versus polar orbiting satellites versus no satellites? And so we just, as a first crack, started looking at air quality alerting. And how would air quality alerting change if we had geostationary PM2.5 estimates versus polar orbiting satellite estimates of PM2.5? And what would that mean in terms of people taking avoidance behavior to avoid that PM2.5 exposure and then reduce their health outcomes? And Kate calculated that there would be about 1,200 premature deaths averted by the additional information that we would get from a geostationary satellite included in our air quality alerting system. And that translates into about $13 billion in healthcare costs and lost economic productivity saved if you had the geostationary versus polar orbiting satellite information. So I just showed 3 ways that these novel geospatial data are increasingly capable of providing actionable information to assess and mitigate air pollution health impacts. And I really think that we're sort of in a whole new world of data availability that can enable us to address air pollution and climate change together and achieve multiple benefits for public health. And most importantly, my acknowledgements, that many people are contributing to the data sets and methods and tools that we're using in this research. It would not be possible to do this research without their contributions. And I particularly appreciate those who are contributing to developing open access data sets. Thank you very much.
All right, so we can have the presenters go sit in special chairs. And then we want to start off with some questions.
Thank you. Thank you very much. Both fascinating discussions. So I'll start in reverse. It is unfortunate that your zip code appears to determine your life expectancy and your total health burden. And the question I wanted to ask you is, what are we going to do about it? I mean, what are you hearing the recipients of your information think about? What are we going to do about it? And it's interesting you mentioned the Volkswagen settlement. Being from California, I'm very familiar with that. I actually played a role in that issue. I'm not clear how you would use those investments to solve these issues that presumably have to do more with incompatible land use than anything. I don't know if you can offer some thoughts.
Yes, thank you. Great questions. The way that the settlement funds were being discussed in this case was to replace diesel burning buses with cleaner burning fuels on bus routes that go through disadvantaged communities. But I think even more broadly than just DC and the Volkswagen settlement funds, that's the point of the Justice 40 initiative, is to try to reduce these disparities. And if we're not identifying which communities are disproportionately burdened accurately, then that really affects our ability to address the problem. In the back to the case of DC, actually, a lot of the PM2.5 mortality risk disparity was driven not by the PM2.5 concentration differences across the city, but by the susceptibility of the population. So we have to be thinking broader than just air quality. It's possible that there's larger PM2.5 disparities than we're currently capable of capturing with our scientific tools. But I think it is very eminent across the entire literature that the susceptibility of the population plays a major role in who's experiencing damaging health outcomes as a result of pollution. So this is a broader societal problem than just air pollution. We need to think about quality access to healthcare. In that southeast quadrant of the city of DC, for example, there's no hospital. There's like people, if you're experiencing a heart attack, you have to go across the city to get appropriate healthcare. And that's just, that's just when it comes to an emergency situation. There's a lot of other drivers, social determinants of health that are contributing to that life expectancy differential as well.
Yes, that was a great answer. The one part I'll add to that is that I do believe that by dissemination of information, one, drawing attention to the importance of outdoor PM2.5, as Dr. Anenberg started out with her talk, and then second, interactive tools that can help people understand the effects of PM on their quality of life. So for example, the OECD has a regional well-being index that is interactive that includes PM2.5 information. And a user can thus click on where they live or where they might be thinking of living and look at the different determinants of the quality of life in that location. I've only seen that at the global scale, this particular interface, but there might be opportunities to disseminate that in other interfaces elsewhere.
Right, a question over.
Hi, is it on? Is this on?
Yes.
Yeah. Okay. For those who don't know, I'm involved in the generation of some of the satellite aerosol products, and I think it's really wonderful that over the last couple of decades now we have this pipeline where the NASA products can go into processing by Randall and others and get used by you and others for all this really great work. I also really like the maps that were shown earlier by you and just now, showing the importance of the resolution. And we're always trying to push our reliable retrievals to find a resolution, but I've had like a long-term concern, which is we know all of our retrievals, the biggest error source, especially in like typical conditions, is quantifying the surface reflection. We also know that some of the most difficult places to do that are cities, because you have some green areas, you have buildings all different shapes and sizes. Cities are often, they're near rivers, they're near coasts. All of these mixed pixels, they're awful. There's 3D effects we just can't model. There's crazy shadowing. And so I have this concern that some of what we see when we go from these fairly coarse resolutions to these finer ones for a kilometer or so, some of it is artifacts which don't average out. So then I kind of wonder, how does this propagate through to the PM estimation? How does it propagate through to the attribution? It could be masking some things, or it could be hiding some things. I kind of know, since you have some sort of, it's not a simple AOD to PM click and go. It's almost like another inversion that you can somewhat account for that. But I guess this is all a long-winded way of asking, do you feel that we can, or rather, what is the level of like credible statements we can make about, this zip code versus that one? Do we have any credible error bar on detecting differences across a city? And if we don't, then what information would you need from us satellite providers to be able to get one? Because I think that seems to be the next frontier, because we have these systems, it's working and it's being used.
I guess that one's for me to start with. And Andy, it's a tough question. You know that as well as anyone. Rob Levy as well has been thinking about this challenging space in assessing resolution. I'm hearing this feedback. I'm going to keep this further away. This dependence of PM2.5 upon spurious reflectance. So I think one way forward is guidance from you on what is the association of uncertainty with reflectance on, I guess they won't hear me online.
Is the other microphone on?
Here, Randall.
It does, okay. Okay. Association of aerosol optical depth with surface reflectance for those different types, and help us to better represent that uncertainty that are inversely weighting by error with respect to AeroNet is more at a broader scale. Can we do something more intelligent about within city variability in order to characterize that uncertainty? Is part of it. The other information source that is growing in availability is ground-based measurements. And those provide us perhaps the best measure of truth. And the ways in which that is becoming useful is both through the direct measure, historically through, let's say, a regression, land use regression type that Dr. Anenberg has been involved with, or more recently with some other statistical fusion that could be through machine learning that helps to reconcile errors in the geophysically based estimate and then correct that with ground-based monitors. Now, that in itself will have its own sources of error that will depend upon monitor placement and the representativeness of that monitor with surface type. There's no easy answer for me to respond to a challenging question like what you said, but I think it gives us a challenge to work forward and towards. I don't know if you have more you want to say.
I have very few additional insights to add to this. I think it's a great question, and I appreciate learning from people who are developing the data sets that we're using. And I do think that it's useful to think about integrating multiple data sets, including from these, a lot of cities now do have these distributed networks of sensors on the ground that perhaps could be useful to integrate as well, learn from that.
I have a question. You want to go?
I just wanted to ask what you think about the importance of speciation as so both your product, Randall, and also your calculations, your health research.
Oh, great question, Brian. I can start. I think speciation would be extremely valuable in two ways I'll talk about it. One is in environmental justice. We know that some species are shorter lived in the atmosphere, more tied to local emission sources within cities. And so if we're really trying to get a sense for which communities within individual cities are overburdened by, say, traffic-related air pollution, having black carbon information that, with that full geographical coverage and high spatial resolution that I was talking about would be very valuable. And the other context is for health. We actually are seeing a grand experiment around the world in how PM2.5 composition is changing. And I don't think we know what that means in terms of changing PM mortality relationship. As we're bringing down anthropogenic emissions and wildfire emissions are increasing and dust emissions are increasing, partly driven by climate change, we're seeing a different PM mix. And what does that mean for PM mortality? I think it's still an open question.
Yeah, I agree. That's also a great question. I'll describe a few ways in which composition is important. One is that it provides a test of our representation of model processes involved, either in the relationship of AOD to PM2.5 or some other parameter that is being simulated. It provides a more robust test of processes than mass alone would be. In the area of health effects, I think, indeed, there may be a greater association of one component versus another, rather than another versus a specific health outcome, and that could help inform strategies to reduce our burden of health effects. Another way I like to think about composition is the role of specific sources in affecting ambient concentrations, in that maybe it is the component that is a driver of the outcome, or maybe it is the source that carries additional components that are not readily measured, elements, heavy metals, that may, or PAHs, something that may be associated with the source. So when I think of composition, I think of both the chemical components as a chemical modeler or as the sources affecting that PM2.5. So those are a few ways in which composition might be useful.
Hello. So I was curious when presenting these PM2.5 products and kind of talked about it earlier, this stacking of uncertainty throughout the processing process. How do you communicate accuracy uncertainty to end users when presenting these final results?
I'll start. Characterizing uncertainty is, I'd say, as challenging as estimating the concentrations themselves. We have recently gone through a formal exercise of assessing the uncertainty in our PM2.5 products and then make those uncertainty estimates available publicly together with the estimates. There is uncertainty in those uncertainty estimates, and that, of course, gets difficult to characterize, but it is a large undertaking. Again, both Andy Sayer and Rob Levy have been involved in that work towards characterizing uncertainty and giving quite thoughtful and useful guidance on how we might think about uncertainty. I'm sure we can do better, but we are endeavoring to make those numbers available.
I'll just add that I think it's useful to have multiple approaches for estimating exposure. So the satellite-derived estimates are one way. The ground monitors are another way. And if they're all pointing in a similar direction, then we can have pretty good confidence that we're getting this approximately right. When it comes to communicating the air pollution attributable health impacts, the uncertainty in the concentrations is, of course, one important element, but we have found in sensitivity analyses that the choice of the epidemiological relative risk estimate matters a lot more to the outcome. And so, in a way, I think we have advanced so much in our ability to assess exposure. We have not really seen the same level of advances in our ability to capture the concentration response relationship that people all over the world are experiencing, as well as the baseline susceptibility that people have around the world. In fact, the baseline death rates and life expectancies continues to be a major limitation in providing useful information to stakeholders. So I think just, there in some cases we can quantify uncertainties. In other cases, we look at sensitivity analyses to try to bound our understanding.
So I'm glad you presented, Susan, on the nexus of climate and air pollution, and also maybe not directly as much in that, but environmental justice is tied into that as well. Because there's been this thing that's been troubling me about climate future, and that in the C40 analysis kind of gets at this a little bit. As we decarbonize and we take down aerosol, this is great for health locally and regionally. But if we get rid of anthropogenic aerosols through decarbonization, we're going to warm by like a watt per meter squared, 1 watt per meter squared or so. Yet our CO2 forcing is going to, at best, level out for decades. It's not going to come down. So if the climate sensitivity is about 0.8 C per watt per meter squared, that means we warm by 0.8 of a degree because of decarbonization and getting rid of aerosol. And I've been wondering, this will have this global effect, coastal regions, low income regions that are impacted by a climate change of about 0.8 or 1 degree Celsius. Have we started thinking about how, when we are doing our impact assessment, we have these local benefits from the PM reduction, decarbonization, but then there's this additional climate penalty from the reduction of aerosol that is global. Have we begun, and this may be for Chris too, have we begun starting to think about that it actually is one more dimension?
Yes, this is a great question, and I think has been a major motivating force for the Climate and Clean Air Coalition to reduce short-lived climate pollutants. The Arctic Monitoring and Assessment Program is working on this as well, that as the world reduces PM emissions driven by health reasons, that's bringing down sulfate quite a lot and unmasking warming. And we need to be taking an intentional approach to also be reducing those short-lived climate pollutants that are warming in the near term at the same time. So making sure that we're reducing black carbon, making sure that we're reducing methane, where the cooling benefits of those are experienced more immediately than the CO2 benefits.
I'll add that perhaps an alternative way of thinking about that is to flip it as an incentive. So in other words, decarbonizing is challenging because it is this amorphous objective that appears not to directly affect a person at one time, and it can be put off. Let's just put it off for another few years. And I like to think about air pollution as something that has an immediate benefit to oneself, to one's family, and therefore may be an incentive that helps to accelerate the decarbonization activity. Now, I know that's not quite the question that you asked.
I agree with that in a region where you have high PM, but if you're in the Arctic or something, where your PM is 3 micrograms per meter cubed, you see in the upcoming decade or two a penalty. And I don't think it's actually being considered in our cost value analysis, but yeah, certainly locally, it's a big win.
Yes. It's complexities in different areas. Yeah.
So yeah, I guess one asking provocative question now. One is now that this that PM 2.5 and other gases as well is something that can be seen by satellites and can be seen globally and possibly can be seen more locally and assigned concentrations with maybe uncertainties. When does it become like kind of used for regulatory reasons? Like I'm not quite ready to consider ourselves good enough to do that. I'm not sure we want to do that. I'm curious where we're going.
You have something to start. I'll keep it.
Well, this takes me back to when I visited Randall Martin at Dalhousie University and met a lot of his colleagues, some of whom were engaged in air quality monitoring. And they said, "You're using our air quality monitoring for what? They're way too uncertain to be used for that." And it just, really helped me realize that we all know the uncertainties of the technologies that we're comfortable with and that we use. And again, if we have multiple data sources that, have completely different methods, completely different technologies and approaches that are pointing in the same direction, that can be very powerful in terms of our confidence level. You asked about regulatory approaches, and one of my favorite activities is thinking about ways that we can integrate satellite data into EPA activities. And I think that, we are somewhat stuck with the Clean Air Act that we have. But that doesn't mean that we're limited in how we use satellite data more broadly. And there's so many different applications. I think Tracy and others answered this question earlier today about ways to integrate satellite data into EPA activities. Helping, to understand where, using satellite data to help understand where the emissions are coming from, getting a better understanding of which sources are contributing in which locations to which health outcomes and to which communities. That can provide really, really valuable information without, saying that we have to flip the entire, regulatory monitoring system on its head. But I definitely think that we need to recognize the limitations of the monitoring system that we have, both in terms of treating it as, lacking uncertainty, and also treating it as capable of providing high quality exposure estimates for people everywhere. It doesn't. That's not what it was intended to do. It was intended to provide estimates of regional air pollution, how those are changing over time. It was not intended to be used for any kind of community scale exposure assessment, for monitoring environmental justice. And so I think that we need to, find ways to supplement the regulatory system that we have legally with additional very valuable information from satellites and other sources.
I love being up here with Dr. Anenberg because she can come off with these amazing responses and it gives me time to think of a response during that time. So thank you. The one anecdote that I'll add to that excellent response was the opportunity to use satellite remote sensing data to contribute to a body of evidence that could inform regulation. And so the specific space in which we've been thinking about a lot, and mostly led by colleagues, is in the shape of the exposure response function at low PM concentrations. And the reason why this is valuable is because in order to probe that shape, one needs to have an exposure assessment that spans a country, a very large domain with a large number of subjects in order to probe that shape of that relationship. And again, it is uncertain, but it can contribute to a body of evidence. And places where it has contributed already is in the establishment of a PM2.5 long-term standard for Canada. It has contributed to a body of evidence about lowering the World Health Organization guideline from 10 to 5 micrograms per cubic meter, and may be contributing to some of the more recent EPA assessments for considering lowering a standard. So it's not as if one is relying solely upon the remote sensing data. It's certainly augmented with ground-based measurements, as well as from other bodies of evidence that a regulatory body should be considering, but I like the fact it can contribute.